All right, did you bring, I haven't written a title here yet. Did you bring some work?
I mean, we haven't gotten too much work. Got my dad's birthday present here.
Oh, what is it?
It's pretty dope. So, it's a mountain biking hat. But it looks like a baseball hat.
Oh, is that a mountain biking company? Deity? I haven't actually heard of them.
It's just like components. And then I got this sick plasma lighter.
Is that a plasma lighter?
Yeah.
Those are cool. I've seen the like stick ones before, but like the Zippo style.
Yeah.
Is he a camper and biker?
Not really, but I just thought, well, he stopped biking.
Okay.
Maybe that hat will inspire him.
Yeah, there you go.
And then I just thought the lighter was sick. So.
Yeah. Do you bike?
Yeah, I bike.
Downhill or mountain bike or cross country?
I just mountain bike, downhill bike.
Yeah.
Like trail bike.
I got you. What kind of bike do you have?
I have a Transition Spire.
Spur. Same.
Spire.
Spur. Same. I have a Transition Spur as well. It's
The
Transition
purple,
Spire.
The purple one?
I have Seafoam Green.
I have Huckleberry Purple.
Is it called? Are you thinking of one called the Spire? Because mine is called the Spur.
I'm pretty sure it's a Spur and a Spire.
Is there? Okay.
We gotta look this up.
I'm surprised football isn't up on this right now. So let's see here. Transition. That's hilarious. I love my Transition. It's like the dopest bike I've ever had.
So much value.
I grew up racing cross country on the cartails. Yeah. So this is the bike I have. So getting the full suspension, but for still the aggressive uphill is like the dopest thing ever.
I have different suspension setup.
So you probably have. This is the most cross country focused.
Okay,
bike.
yeah, no, it's not.
So you probably have.
It's like it's new, too. It's like
that's pretty. There you go. Oh my gosh. You're like Spire. I'm like Spur.
No,
you're wrong. It's Spur.
It's not the Fox suspension. It should be the RockShox. Where is it? There it is. Except purple.
That same purple color.
Yeah.
This. So yours is a touch more downhill focused. But you can still have it uphill.
Yeah, exactly. Because I go downhilling a lot. Mm-hmm. But I also enjoy going to new places and doing stuff. So.
Yeah, and like not just having to have a lift wherever you go. Exactly. I mean, this is more suspension than I've ever had in my life because I've just ridden hardtails.
So are you like cross country?
Like I was growing up, and now I'm having so much fun on the downhills, like faster than I've ever ridden downhill before.
Yeah.
Just like, whoa.
You can go so much faster.
Like, I can actually do it, and then the drop post is like,
yeah.
Transition's a dope company. I just found out about them this year.
Do you have carbon?
No.
Yeah, I feel that.
My old one was carbon and it lasted 7 years, which was awesome when I'm here. All right, let's see what math is going on.
So this is the note sheet, and then I gotta get on my computer.
Yeah, no worries. Assuming that it's on the same topic, essentially this is practice, so that when you do go home and work on.
This isn't in the GoPro's way.
When you do go home and work on these ones from the textbook. Ideally, we'll be getting the same skills learned here, right?
Okay.
This isn't the textbook, is it?
No, this isn't. This is just a random worksheet. So we're back.
Right, so we're doing slopes of lines. Nice. Slopes of lines. Super, super crucially important topic, actually. This is one of the fundamental basis of calculus.
Okay, yeah, I remember what we're doing today now. We're doing a little algebra with it too.
Yeah, definitely. Some fraction work, some like minusing and fraction and stuff.
Okay, so I guess we can even zoom in if we want. Use slope formula to determine the slope of each line. Okay.
You want to start with that first one?
Yeah, sure. I don't even know where to start. We haven't done problems like this yet.
Okay, that's fine.
So A, B. We're finding the slope of A to B. That's a 0, 1, 2, 3, 4. It should be 0, 4, right?
So we're going from A to B, which is right. -1, -4, which is like right here, and then to B, which is 2, -4. And then we have some line that does this.
Yeah.
Okay. This is A. This is B. So what do you suggest the answer is?
0, I think. And then, or no.
Equals slope?
Equals slope.
Is that what you're saying? 0 equals slope?
Yeah. The slope is 0.
Yeah.
It's just flat line.
There you go.
What's it called? Is that like undefined or What's the other one?
So there is a slope of 0, which means you are not rising or falling any amount.
Oh yeah, but when it's on the y-axis
for every step you go over.
Yeah,
And
it's
then
like a straight line, right?
A vertical line?
Yeah, a vertical line.
Right, because there's no, like, basically what a vertical line means in terms of slope, since slope is, you've heard this before probably, rise over run.
Yeah.
Right? Meaning change in y, change in the up and downness, divided by the change in left to rightness.
Okay.
When you have a vertical line, you're going up an infinite amount and over 0. So now you have the question, how many times does 0 go into infinity?
0 times?
It goes in an infinite amount. 0 plus 0 plus 0 plus 0 plus 0 plus 0. You could just do that forever, right?
Yeah.
This is a slope of infinity, but you can't say slope equals infinity because infinity isn't a number.
Yeah.
So you know what word we use to describe that? Undefined.
Okay.
Undefined means you're going up an infinite amount and over 0. Okay. Now in this case, you're going up 0 and over any amount, any infinite amount.
4, right?
Okay.
Yeah, I think it's
4. Yeah, and from A to B specifically would be 3, 1, 2, 3.
Oh yeah.
Up 0 over 3, up 0 over 3. What is 0 divided by any number?
0.
0, right? Because basically this number goes into 0 times. A little quirk of math, moral of the story here is when you get a flat line, it's got a slope of 0 because slope is always talking about your change in y as you move in x. Vertical line, infinite over 0 or undefined. So we kind of got off on a slight tangent there because you just answered this original question so quickly.
Yeah.
Right. All right, now let me do this, make kind of a bigger graph.
This next one looks more interesting. C to D.
Yeah. Get like a bigger graph going here. Cool. So C to D, -1 comma 2, and then 2 comma 0. So the question is, how much does this rise or fall for every 1 unit it moves over?
It goes up 2 and then over 3.
I think you're right on point. I'm just making my line look a little nicer there. All right, so you said up 2, so I'm just going to start. Which point are you starting at?
I started at C.
At C, which is over at 5 comma -2 right here. Okay, and you're saying up 2, and then what?
Over 1.
Over left or right?
Or over 3.
1, 2, 3.
Yeah.
Almost.
1, 2,
3. Oh, you know what? It's because
1, 2,
I drew it wrong. Did I count that right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's why. My little. Just back it up here because that was one of the last things I did. There we go. So that's C, D. So you said up 2 over 3. So yep, that's up plus 2 to the right or left?
To the left.
So positive or -3?
Negative.
Okay, so we could say our slope is equal to rise over run, or our change in y, over our change in x.
Yeah.
2 divided by -3?
Oh my god, whenever there's negative, just throws me off.
The negative's a little weird.
3. Why can't I answer this question?
What is 2/3 of a dollar? How much money is that?
2/3 of a dollar? 2/3 of a dollar. I don't know. I only know like fourths of a dollar.
Right. So it would be like 66 or 67 cents.
Okay.
Roughly. That's what 2/3 is. It's 0.66666666 and so on. 1/3 is 0.33333333.
Okay.
So 2/3 is whatever. I'm just going to keep it as 2/3.
Okay.
That's fine. In fact, with slope, fractions are almost always more useful. And I'm just going to bring the negative out front, and you're going to see why this also works. You know, you went up 2 and left 3. That's fine. Whenever I do slope, I always, just keep it consistent. I always move from left to right.
Oh, okay.
Okay, so when I move from left to right, let me start at like D, for example. We'll go down 2 and then to the right 3.
So it's -3 and then +3. Or -2 down.
2 down. That's our fall.
Yeah.
Or our rise, I guess. -2 over. And then how much over?
Over 3.
Over 3.
Positive. So then you don't have to do that extra step.
Right. In this case, the negative ends up on bottom because you went left. If you always go right, you always move right, then your negative will never end up on bottom. And on top is where you get to decide, is your slope moving down or is your slope moving upward?
Yeah.
In this case, if you put a ball right here, what would happen to it?
It'd roll down.
It'd roll down.
Yeah.
It would go down 2 feet for every 3 feet it went to the right. Okay, so it's not quite falling down 2 feet over 2, down 2 over 2. It's a little flatter than that.
Yeah.
But still, I don't know, it's kind of steep. One last thing to see on a problem like this, which is totally fine to do, is let's go from D to C.
D to C.
Okay, so how much do we go down? And let me just lightly erase some of this here.
1, 2, 3, 4. And then, so down 4. And then 1, 2, 3, 4, 5, 6. And over 6.
Over 6.
Down 4 over 6.
Okay, so
which makes sense because we could just double that. Or double our first one. It makes sense.
Yeah, 4/6 of a dollar.
4/6 of a dollar? Oh, God.
Is also the same thing as...
Oh, it's 0.6?
It's 0.666, right? Just for fun. Okay, here's 1/3, 2/3, and 3/3. Or 1/6, 2/6, 3/6, 4/6. 4/6 is the same as 2/3.
4/6. Okay, yeah.
Right?
Yeah.
Leaving behind 2/6, aka 1/3. Right? This is just a fun little thing with fractions.
Yeah.
Basically meaning 4 compared to 6 is the same ratio as 2 compared to 3.
Yeah. My quick math is not that good.
You're fine. The fractions are honestly something that most students feel embarrassed to not admit that they don't understand at a deep level.
Yeah.
Because you learn them in like 4th grade.
Exactly, yeah.
But they don't make sense in 4th grade because you don't have like what is miles per hour when you're a kid. You can't use like real life examples that help your brain that much.
Yeah.
But then teachers in 6th grade and beyond just assume you know fractions. And I promise you there's a sea of students out there who could look at this and not intuitively really know what 4/6 means.
It's like a dollar or something, yeah.
Right, exactly. And fractions are hard. Anyway, they're cool because they're relative, meaning you can do that shape, you can do this shape, or you could even do this little shape right here. Check this out. How much do you think we go down moving over 1? So this is +1 over. How much do you think we go down in that little tiny triangle?
0.5? It's an over 1. 0.66, okay.
That's because it's down 2/3 over 1. Down 2/3 over 1. Down 2/3 over 1. That's exactly what this. Down 2 over 3 is the same as down 2/3 over 1.
Yeah.
Well, big problem there. We just did a lot of math for one simple problem. All right, let's see. I'm going to draw the chart for you and then let you just go to town on the iPad here.
Oh, yeah. I got all this stuff and I didn't even...
And I think I can do... Let me zoom in so you have bigger squares to work with. you got to plot everything.
Okay.
Pick, yeah, maybe 3 is more interesting than 4.
3? Yeah, let's do 3. F4 is a little boring. Okay, so 0, 1. So this is. Oh.
Yeah, I figured out how to make the tap thing work again. There you go. That's fine.
Good enough.
That'll do.
Then E. And F is over. Hold up, what? It's over 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then up. 1, 2, 3, 6. 1, 2, 3, 4, 5.
Oh, we'll just pretend that.
6.
Yeah. And if you want to circle, you could bring it down 1 row, unless it doesn't matter.
How do I do that? This
So circle the whole graph, yeah. And then just,
F
you can get F in there, and then just bring it down 1 or 2 is fine, yeah.
Cool.
Now fix your F.
Yeah.
You F'd up your F.
Okay. Boom. F. Oh, now it's still thrown off.
Yeah, it was just barely below where it's supposed to be.
Okay, so
It was 5.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6.
Cool. All right, and now draw your line, which takes some dexterity.
Nice. Cool. Arrows.
We'll call that top
No
of
idea.
arrow, I guess.
Okay. Perfect.
All right, there you go.
All right, so we'll go from right to left, I guess. So we'll go over 1 and up 2. So over 1, up 2.
You did just say right to left. I think you meant
Or left to right.
I think you meant left to right, right? And by the visual, that makes sense, right? Up, 1 over 2. Oh wait, up 1 over 2. Wait, up 1 over 2. Up 1 over 2.
Wait.
I'm veering off track here. It's rise over run. So how much do you go up? Every time you go over 1.
Yeah, you go. I see. So up 2 over 1.
Cool.
Cool.
Yeah, change in y, change in your up and downness,
Or
divided by the change in x, which we try to just say, keep it 1, makes life easy. Okay, up 2 over 1. Up 2 over 1. In fact, grab that little laser pointer and track it. Up 2 over 1.
2 over 1.
Up 2 over 1. Up 2 over 1. Okay, and just for the sake of it, go ahead and do the same type of calculation, but use the points E and F. So how much do you go up and how much do you go over?
1, 2, 3, 4, 5, 6. 1, 2, 3. So up 6. Oh, whoops. Up 6 over 3.
Yep.
Which makes sense because that's double that.
Exactly
6
right.
is double 3, 2 is double 1.
Exactly right. And if you simplified this, what is 2 divided by 1?
2 divided by 1, 2.
2. And what is 6 divided by 3?
6, 3.
How many times does 3 go into 6?
2.
2. How many times does 1 go into 2?
2.
2, right? And this could also be up 8 over 4. You'd be right on the line. Up 100 over 50.
Yeah.
You'd be right on the line. Up 10 million over 5 million. That would end up, like literally that point would get perfectly intersected eventually.
Yeah.
As long as the y value is twice as big as the x value.
So that's the next episode. Going to 50 million.
Yeah, we're just going to zoom this thing out really, really small. Yeah, I mean, slope is not too tricky, but it's actually extremely useful.
Yeah.
For determining things like speed, like the amount of money you expect to make monthly and such, because you could have a graph that's money by time, and if you know how much money you're making per time, you know your hourly wage or your salary.
Yeah, exactly.
Speed of cars, and then slope gets really fun when your graph, instead of looking like this, starts to look like this.
Yeah.
And now you're finding slopes at individual points, knowing that the slope at every point is going to be a little different than its neighboring spots. That's calculus.
Okay.
Anyway, we don't have to do that. But it does expand from just literally doing rise over run every time. Because I know it gets boring. But anyway, let's keep with the boring. Let's make a new little section down here.
We can just get 4.
Yeah, 4. What's the answer to 4?
4, it's undefined.
Undefined. You go up infinite amount.
And over
0. That's called going like 10 million miles per 0 seconds.
Yeah.
Which, can you do that?
No.
Quantum particles might be able to. But they're pretty undefined as we know them anyway. So.
Quantum particles? What's a quantum particle?
Like the little specks of existence that make up protons and neutrons and electrons.
Yeah, exactly. I've always thought about that. Like, atoms are made of protons and neutrons, right?
Right. You go one step further.
Like what's after that? You know.
We have a word for a lot of them. They're called fundamental particles, or the things that make up protons. Quarks.
I've heard of quarks
before.
Quarks,
right? Maybe leptons.
I haven't heard of leptons.
Okay, maybe like the Higgs boson particle.
No,
that's called the God particle.
Sometimes I'll watch the videos about that kind of stuff.
Yeah.
I kind of forget a lot of stuff. I remember quarks though.
That's fine. I've watched
deep stuff.
A million of those videos, and every single time I get a little more of an understanding.
Exactly.
But basically, you have your classic model of an atom that you've seen before, right? Some protons, some neutrons, some
electrons. We're learning
atoms
in biology right now. We call the basic atoms.
And that's cool because you're probably learning organic chemistry, so carbon, oxygen, hydrogen, and nitrogen. It's what makes up 99% of everything in existence.
Yeah.
This is like this classic model of a particle that we've all seen before. But when you do zoom in on this proton and neutron kind of glob in the middle, and even zooming in on an electron as well. Electron is a quantum particle. When you zoom in on these, they're actually made up of little infinitesimal, meaning 0 space. They take up 0 space, but they have a lot of, that's too big of a line. They have a lot of energy.
So they take up 0 space. But then how does them added together make space?
Think of it as like throwing, this is a super basic way of explaining it. Think of throwing 3 magnets in a bin that might attract or repel depending on their orientation, but those magnets take up no space. They still have the energy to attract and repel in those infinitesimal points. Okay. However, there's no mass there to actually
that's weird.
Take up space.
To think about.
But it's crazy, but it's actually less crazy when you think of Einstein's equation here, which there's actually an additional part. We won't talk about that. No one ever talks about that.
No way.
But E equals mc squared. C is the speed of light, which is a number.
So energy equals mass.
Boom, you just said it. Energy equals mass.
Energy equals mass.
Times some number.
Yeah.
Therefore, mass is really just a property that manifests from a lot of energy being tightly wound together. And suddenly a thing that isn't a thing
with enough no things becomes a thing.
Yeah, it's trippy.
Yeah.
Right. So quantum mechanics is undefined, back to what we were talking about originally.
Yeah.
Because you can't really define what's going on here. You can just make rules for how the system generally works.
Have we even seen an atom? Have we been able to zoom in enough to see one? Because I'm not sure if that's a common thing or if it's never been done before. This
is probably the most famous picture of something that someone would call taking a picture of an atom. This right here.
Huh.
It's the energy that hydrogen is giving off.
Yeah.
Here's your electron orbit. Here's your proton and potentially neutron if this is a stable.
Is that the inner electron orbit?
Yeah,
or the 2 electrons? Because there has to be 2 electrons and then everything else.
Exactly. And technically there's even more orbits out here that are so low energy that the electron or the charge of negative energy is most likely going to be here, occasionally here, very occasionally here. Shows the atom's electron orbital. Yeah, and then you see this word wave function.
Yeah.
Which is literally what it sounds like. It's some function that looks like this.
Nuts.
But really what it is, it's not, this is a 2-dimensional version. What you're really seeing is, how can I show this? It's really just a spiral. that you can imagine.
So like that?
Yeah, imagine instead of looking straight down the spiral, imagine looking at it perfectly straight on.
Yeah.
So now you have waves. There's a lot to quantum mechanics.
Math
Math is super helpful for quantum mechanics because we can't directly touch these things.
Exactly.
So we just have to do the math and trust that it works, and then run experiments, like building an atom bomb, for example. And yeah, it works as it turns out.
It does work.
Okay.
Atom bomb is literally just splitting an atom, right?
Yeah, there's fusion bombs and fission bombs. An atom bomb, as we know it, is a fusion bomb bombarding atoms together.
Okay.
And then there's a fission, or I think I just got that backwards. You hear of atom bomb and you hear of nuclear or hydrogen bomb.
Yeah.
One of them involves splitting giant particles into smaller pieces. The other involves taking two small pieces and shoving them into one big one. Both create expansive amounts of energy in a chain reaction that's explosive.
You know that movie where like they're like spinning these atoms to like come up with some like make like a portal or something. Do you know what I'm talking about? It was some superhero movie.
Oh no.
It was like
superhero movies have been playing with the multi-universe quantum mechanics theme a lot in like recent years, which I think is cool. I have a cousin that's 9 that talks to me about quantum mechanics every season in Marvel, and I'm like,
hell yeah.
Whoa, like, I didn't even think about this stuff in college.
Yeah. Anyways.
All right, back to math.
Slow.
We're not editing that out. That's staying in.
Yeah, that's staying in. It's good content.
Okay, so now we have something a little different. You go ahead and read this, and I'll start to make the graph.
Okay. Graph each pair of lines. Use slopes to determine whether the lines are parallel, perpendicular, or neither. Okay, so we'll do 5 first.
Nice. It's a good little mix of what we've been doing over the last few sessions.
So IJ.
I'll just let you get after it. Here, I'll make your life a little easier for the viewer because you probably wouldn't do this. Just put some tick marks on there because you would just probably count.
Yeah.
Which is fine. Oops, not a 5.
IJ.
All right. Have fun.
Okay, so I is okay. Okay, sometimes I forget. You go up and over or over and up?
So yeah, this is the reason you're forgetting is because slope is always rise.
Yeah.
Over run.
Yeah.
Coordinate pairs are always x
over
comma y.
Okay.
So you move.
Sometimes that always trips me out. I mean, yeah.
It will continue to, but you'll get it.
Yeah. Okay. So over 1, or over 1, and then you just stay there. So
yeah, exactly.
First point I, and then second point J, which is 5, and up 3. And then K, which is over 6, and then up or down -1.
Sorry, I kind of got up in your business with that 6.
No worries.
All right.
Okay. Now what?
Which lines are they referencing?
Oh, then we need to do L2, which
Okay.
is 0. Huh? Okay, 0 and then up 2, which is L. Okay, so find the slope of L or I to J and then K to L. So like laser beam there to there.
Got those 2.
Cool.
Okay, now not laser beam.
No, yeah.
You can draw your lines in if that helps.
Yeah. Okay.
Now check this out. Do that, and then you
This
got
thing?
it. Yeah. So circle it, tap it, resize.
What?
Resize, and then that's your option to rotate down there.
Rotate.
So you can like rotate and move at the same time. Yeah, exactly.
Swag. So then hopefully this one's first try. Yeah. I'll move it just for why not? Size. Oh my god. Nope.
Yeah.
Well, I guess I'll try again.
That one's probably gonna be still a little high. You got it.
I'll get it.
You're gonna get just as good at this as I am.
Use Sub Pro. And up. And over. That looks good. Cool. Okay, so we need to find use slopes to determine whether. Okay, so we need to figure out if these two are parallel, which I don't think they are.
They're not parallel.
Perpendicular. That's possible.
It is possible, right? Show me perpendicular with your hands.
Perpendicular is okay. It's not perpendicular. Perpendicular is that. Cool. So it's like 90-degree angles.
Yeah. And we're gonna find the slope.
So I mean, we know we have to find the slope, but we know it's not. Yeah. Pretty obvious.
I'll show you the test to mathematically determine if it's perpendicular.
Yeah.
And you're gonna see why it's close, but no, not like exactly perpendicular.
Okay.
But you can go find your slopes.
All right. So slope for it's 1, 2, 3. So we'll do 3. 3 over 1, 2, 3, 4. 4. And that's for IJ. J.
Cool.
Little funky J.
We like to use, just for future reference, generally the letter we use for slope is M. So if you want to write M, and then M equals
M
3
equals
quarters. Yeah, exactly. Okay. And then here, let me show you one last little thing. Just kind of adjust this really quick. This is like a way to put all that notation in one.
So, wait, could you do measure IJ? Yeah.
So the slope of IJ, this is called a subscript, or it's just like additional information.
Yeah.
Is 3/4, and then M of LK will be a different number.
Get rid of this rookie stuff. Okay, so then that's that, I guess. And then for LK, so measure LK is so 1, 2, 3, 3, and 6. 3 and 6. So they're not perpendicular. If these are the same, would they be?
If they were the exact same.
This needs to be negative.
Yeah, so that's important.
So if they're the same, would it be 3 over 4 and then negative 3 over 4? Would that like work?
For perpendicular or parallel?
Perpendicular.
So for perpendicular, that's super close. That's a fine guess. It would be the, how can I phrase this? The perpendicular slope to 3/4 is called the opposite reciprocal. And we're going to see it. I'll just do a graphing example so you can see it right after. Slope of what's perpendicular, that's the symbol for perpendicular, makes sense, right?
Yeah.
Equals negative, because we know it's going to be downward, but it's not going to be down 3 over 4, it's actually going to be down 4 over 3. And we can just check that. Let me just pick a point right here. Then we'll go down 1. Here we go. Down 1, 2, 3, 4 over 1, 2, 3. Okay, let's just see how that looks. Does it look pretty perpendicular to that line?
So, yeah.
In that case, it is. I'll give you another example after.
Okay, so you flip it, but okay, I think I get it.
Signs flipped, fraction flipped. If the sign and the fraction are both flipped, then it's a perpendicular slope.
Yeah. Also, another thing. So let's say we do like a random fraction, like 1/2, right? Mm-hmm. When you do this, like just put a negative there. That means just that part is negative, right?
Yeah, instead of going up 1 over 2, you're now going down 1 over 2.
Yeah, right. So then, but when you put a negative there, does that make the whole thing negative?
That's a good question, classic.
Yeah.
A negative out front, let me go to a new page here.
Yeah.
So negative 1/2 could equally be thought of as negative 1 times 1/2. Okay. Which could equally be thought of as negative 1 over 1 times 1/2. What is negative 1 divided by 1?
1 or negative 1?
Negative 1.
Negative
How
1.
many times does 1 go into negative 1?
1. Negative 1.
Negative 1 times, right?
Yeah.
So this is like the way expanded form of this.
Yeah.
But now we can multiply across the top, and we get negative 1 times 1, and then 1 times 2.
Okay.
Moral of the story is if the negative's out front, that's equivalent to it just being on top.
So it doesn't really matter.
It doesn't matter, right?
Okay.
Even if the negative's on bottom, like these two things are equal. These three things are equal.
Huh. But when you graph them, they're different.
Let's see.
Or
okay, I'm going to start. Here's a starting point.
Okay.
Okay, I'm going to go up. Let me zoom in. Start going up 1.
Up 1.
And then left 2. Right there. Okay, and I'll pick a different color. Starting at the same starting point, let's go actually down 1. And then to the right 2. Right there. So that's going to be...
So they're going to have the same slope?
It's always going to be... It's going to create the same slope, just kind of based in a different starting point, but holistically they're the same answer actually. So in this case, same line, same slope, same everything. And then let's just do one more kind of cool one here. That wasn't a very great drawing, but that's okay.
Good idea.
And then this one, negative 1/2.
Yeah.
How about we go down 1/2 and over 1? Negative 1/2 is technically the same as negative 1/2 over 1. If you want to look at this as its own like number.
Yeah.
So going down 1 over 2 is the same eventually as going down 1/2 over 1.
Okay.
Down 1/2 over 1. Down 1/2 over 1.
So. Oh, okay.
All 3 of those things represent the same number.
All right.
Same with this right here, the last number that this is all equal to. That's also fine. You could write that for the slope if you want.
Okay, cool. Because I was thinking about that sometimes and I never...
Yeah, what you're probably get a little confused on is something that looks like this.
Oh, true.
Now you have negative 1 over negative 2.
So that's different to these.
Yes,
okay,
exactly.
So that's the one different one.
Yeah, exactly. This is just equal to. It's the same rule as multiplication.
Yeah.
Divide a negative by a negative. It's like doing a 180 and then turning right back around.
Yeah.
Another way of thinking of it is how many times does a negative number go into a negative number? Well, it's going to go in a positive amount of times because you just add a negative number by itself a couple times to get to another negative number.
Yeah. Kind of weird, a little weird.
You'll get your negatives and positives in time. They're just like fractions, something that everyone is supposed to know, but a high percentage of people surprisingly don't know, and it's not their fault generally.
Yeah.
Also, just real quick, we'll jump into another problem, so I'm sure it's coming up, but have you ever seen this before? Probably in your algebra class?
Y equals mx plus b? Yeah, y equals slope.
There you go.
And then just x, right?
X is a variable.
Yeah.
And then this is your...
y-intercept?
Y-intercept, right. Yeah. But that m, when I said that we typically use m
for slope,
it's the same m.
Yeah.
Cool. You're probably going to do a little bit of that, even though this is geometry class. All right, we got time for one more problem.
Okay,
let's do it.
Check it out. Such.
You're just going to say your password out loud for the camera?
Such. That's all you get.
All right.
It's 1/2.
You have all your important financial documents on your school computer.
Anyways.
Let's try this one.
This one?
This is more fun.
Okay, I'm done. The skiing.
All right. I'm going to read it out for the viewership out there. So at a ski resort, the different ski runs down the mountain are color-coded according to difficulty. And this is actually all true. I looked at this. I was like, what makes a green? Obvious angle.
Yeah.
Green is easy, blue is medium, black is hard. Assume that the ski runs below are rated only according to their slope, steeper is harder, and that there is 1 green, 1 blue, and 1 black run. Assign a color to each run. I don't know why they're using emerald and ruby.
Maybe that's like the name of the run.
Oh, okay.
Yeah.
Diamond, emerald, and ruby are the names of the runs. That makes sense. So you're supposed to assign a green circle, a blue square, or a black diamond to each of these.
Okay, so based on how...
Even though they're not negatives, which is funny.
Yeah, I was going to say, like...
We'll call it how hard
guess
it
you
is
could
to...
ski the other way.
Yeah, how hard is it to skin up?
Yeah.
Same idea, right? Anyway. All right. And let me just write for out there. So we have...
So L4, or... Prize for... Okay, yeah, L4, over 7.
And then what's ruby? It's confusing that they use colors.
I think emerald and ruby are the same.
Emerald and ruby?
Yeah.
4/7 and 5/8.
Yeah. Maybe. I don't know.
Close.
We'll see.
We'll see.
So
you could.
I guess I'll just draw this.
Yeah.
Oops.
All those options.
Fancy. Okay, so
you could zoom in if that helps.
I think it's fine. Oh, look at that.
Nice. On the money. I'm just gonna quickly scroll because I'm curious how much you have. Yeah, it looks like you do some line equations, but that's okay because it sounded like you didn't have too much trouble with that.
Yeah, I think it's fine.
All right, cool. Sorry.
Okay, so 4. 1, 2, 3, 4, and then over 7. 1, 2, 3, 4, 5, 6, 7. Wait, I just realized we don't have like a first. Oh, it's probably coming. We'll just assume it's from 0.
I like that word. You can just assume that as long as you assume it for everyone.
I'll just put that. All right, this will be the special one. I'll do everything else with red. Okay, so that's that one.
Okay.
Oh, just completely missed. Resize. Oh.
Nice.
Cool. And then what's another one? We'll do diamonds. So that's 1, 2, 3, 4, 5, and then 1, 2, 3, 4. Ooh, diamonds. That one's hard. Yeah, that looks right.
Yeah, and don't be afraid to label these lines, even with just one letter might help.
Okay, so this one is emerald.
Cool.
This is diamond. And then up 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. Oh, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we know those two are not the same, so this one's R.
Good luck here.
That's the money one.
Hey, that wasn't half bad.
No.
You're pretty much on it.
Do it from this side. Yeah, cool.
Yeah, that's reasonable, right?
Okay,
pretty close, those two runs.
Diamond is the hardest. Ruby.
Ironically, they even.
Yeah, exactly. And then ruby is second hardest, and emerald is the least hardest because it's green.
Yeah, and in reality,
they literally just gave that away in the name.
I mean, yeah, emerald and ruby might be both greens.
Oh, true. But in this case,
what it really comes down to, this is I've looked this up before. I'm pretty sure the ranges are like
for the actual degree.
Yeah, it's
ranking?
like and it also there's
Sure, I've never thought about how they rank that.
Yeah, there's other variables like trees,
like mandatory
moguls, cliffs, stuff like this. But in general, I think it's under 20 degrees, and then between 20 and
it's like
30, I think, and then like 30 plus, with all of a sudden 45 degrees being like basically where snow can't even hold on to the slope.
Okay.
So that's why this is some super fun stuff to ski, especially in the backcountry when there's powder. It's just like nice and fun.
It's just flowy, yeah.
But like this region, kind of right in the middle here, is super dangerous for avalanches because it's steep enough to slide, but not steep enough to have already
to not stick.
Exactly, to have already slidden. So this is like where avalanches accumulate, is right in between. So if you're in the backcountry and you're skiing something that feels like an easy black diamond and it's awesome, there's higher avalanche risk there than skiing something that's like a gnarly triple black diamond, which is like counterintuitive.
Wait, what do you mean by that?
Because the steeper something is, that snow is never going to build up over time. It's going to constantly fall toward the bottom.
Oh, yeah.
But as soon as you hit like a nice critical angle, now that snow can build up forever.
But then eventually slide.
And if it's something so flat, it can build up forever and ever, and it'll never slide anywhere.
So you're safer just doing like a gnarly, well, in a way, you're safer doing like a gnarly.
You're safer taking your Airy 1 course and assessing avalanches and making wise decisions before you end up in these places.
Yeah.
And then just like...
an avalanche class?
Yeah, I've got mine.
I want to take one.
Super worth it. The school I used to work at offered our school on the weekends to the company that ran the local Avi course. So every teacher at our school got to take it for free, which was awesome because it's like $1,000.
Yeah.
And I took it twice because I was just
we did like beacon training in like 5th grade.
Yeah, that's awesome. I mean, honestly, like enough to inspire kids to be like, maybe I want to do this when I'm older.
Yeah, exactly.
All right, how we do? Is it almost time? It's basically time. 5:54.
5:54.
Let's peek at one of the harder problems just so we can start
Find
thinking about it.
We can.
Okay.
Let's see.
Probably that.
Those are
These
the
all
answers.
Okay,
Yeah.
cool.
That one looks long.
Yes. Would you rather, these are kind of like symbolic. You'll be just fine on these because you just said slope and y-intercept, right? This one's easy. Just crosses a +2, goes down 4 over 3. There's your line.
Yeah.
Okay, so those are easy. This one you might have to simplify slightly and get y by itself because slope-intercept form likes it when you have y by itself on one side of the equation. Not too hard. You have your scroll set up opposite of mine. Now these ones, let me just do one really quick just so you can kind of see it happen. So we have x minus 5y equals 0 and y plus 1 equals 1/5. These aren't the hardest ones, but this is apparently what you do on a lot of these problems, so we'll practice it. We're trying to determine if these are parallel, perpendicular, or neither. Two things you could do. One, you could plug these right into graphing applications and look, that's fine. Or you could plug in a couple numbers like 1, 2, 3, and 4 for x and see what y is, graph it, whatever.
Okay.
Or we can solve it algebraically. So I'll just go ahead and do that. I want to try to get it into slope-intercept form so that I can immediately read the slope, in which case I want to end with y equals. If I want to end with y equals, I'm going to go ahead and get rid of, I'm going to move x and y to opposite sides. So I'm going to add 5y to both sides so that it cancels here. X plus 0 equals 5y. Another way of writing that is 5y equals x.
Wait, so x is equal to 5y.
Therefore,
so the x equals 5?
Not quite. Divide by 5. Oh, sorry. Let me do that in white to keep consistent with my colors. Divide by 5. Divide by 5. Those cancel.
Yeah.
Y equals 1/5 x. Technically plus 0.
So that's our slope.
Our slope is up 1
over 5.
Over 5. And I know that that's slope-intercept form because I have y on one side and I have it equal to an x term and a non-x term.
Okay, so wait, so our b is 0?
Our b is 0. It crosses right at the 0.
Okay.
So this is really our equation. Same thing here. Y plus 1 equals, let me just distribute this through. 1/5 x. What's 1/5 times 5?
Well, 1/5 times 5? Oh, God. Point something, I don't know.
1/5 is 0.2.
Okay.
What is 1/5 of 5 though? What is 5 divided by 5?
1.
1.
Yeah.
All right, so 1/5 of 5 is going to be whatever number you have to add to itself 5 times to make 5. In this case, it's 1. So then same thing here. Subtract the 1. We're trying to get y by itself. Those cancel out. Y equals 1/5 x. So we actually, even though the two equations didn't look the same, they ended up having not only the same slope, but they were the exact same line. Because you can have two lines that have the same slope and don't have the same y-intercept, but these two literally are crossing right at the origin.
Oh, okay.
They're the same.
So the y-intercept doesn't matter for parallel lines?
For parallel, no. Nor perpendicular, technically, right? If it's perpendicular here, perpendicular anywhere, it just matters where they eventually cross. Okay, so these problems are all about just simplifying to slope-intercept form and then reading your slope. Okay, if the slope is the same, what does that mean?
That means they're parallel.
That means they're parallel, and if the slopes are, what's the perpendicular slope for this?
-5 over 1.
Exactly. There you go.
I'm gonna call it my sister.
I think you're good. 559.